Hello everyone, my name is Samuel Dembowitz and I will be talking about our first lab, constant velocity. In this presentation I will be discussing how I performed a real-life observation of constant velocity, how I then created a computer model of that observed system, how I then compared the model to the observed system, and throughout the presentation I will be describing the physics involved in both of these systems. In this lab, we had multiple goals, first of which was to understand Newton's second law, which is that the net force is equal to the change of momentum over the change in time. Now, this fundamental principle is what we use to create the position update formula and the velocity update formula, which we will use to model the system in a computer model with GlowScript. And to get this positional data and velocity data, we will use the software called Tracker. For this experiment, I used a lacrosse ball, which was 0.14 kilograms and 63.7 millimeters in diameter, which was used to initialize the tracker program, as well as create an accurate model in GlowScript. I used a basement railing for my track, which was approximately 122 centimeters long and 12 centimeters wide. This removed most of the z-axis movement, but not all of it, as you will see as we continue. And here is a depiction of the ball moving in the negative x direction, and you can see that there's a little bit of movement in the z-axis here as well. There are a few key features from Tracker that should be noted. The first of which is the orientation of my axes, which predicted the ball's motion in the negative x direction, as you can see in this negative graph here. The positional data from this graph showed up in this table here, which I then used to calculate my initial position and my initial velocity, as well as the time range that I would need in order to initialize my GlowScript program. If I change the orientation of the axes from, say, negative to positive, the magnitude of the vectors would not change at all. However, the direction would, which would flip the slope of the position over time graph and flip the sign of the velocity graph. When initializing my GlowScript program, I utilized the ball's mass, the initial position, and the initial velocity, and the delta t that I used from my tracker program. I also calculated that the net force would be 0, since the change in momentum would be 0, since velocity final equals velocity initial, which is the overall basis of this lab. As you can see, I implemented that into the GlowScript program here. I also updated the velocity and position update formulas based on the ones that we derived from Newton's second law. And you can see the program in action here. You can see the ball moving in the negative direction, a negative constant position slope, and a constant velocity. To create my comparison, I made sure to use the information from both Tracker and GlowScript in order to create a Google Sheets line graph that you can see here, observed position versus predicted. You can see there are some irregularities in the observed position, which I believe is a result of the center mass being blurred in the video, as well as some movement in the z-axis, which I mentioned as a result of the width of the rail that I used. After looking at the comparison, it's clear that there are some ways that it could be improved. On the side of the computer model, including forces like drag and friction would create a more accurate model of the real-life system. In the real-life observation, if I had a better camera with a higher frame rate and extended positional values in Tracker, I would be able to improve the model comparison in the GlowScript. And if I had a thinner rail for the ball, I would be able to reduce some of the motion in the z-axis that created some discrepancies that we saw in the comparison. After looking at the systems and the comparison between the two, it's clear to see that there is a constant summation of forces creating the zero net force that we are looking for in our GlowScript. Many of these components include gravity, the normal force, friction, and drag forces, but there are many components that are difficult to name that make it impossible to create a one-to-one model in GlowScript. In this lab, we learned the application of Newton's second law, the change in momentum over the change in time equal to the net force. We observed when this net force is equal to 0, and we use that information to calculate the velocity and position over time in the GlowScript program. The application of this lab is obviously predicting motion in constant velocity, but we will use these fundamental equations in order to calculate the velocity and position of things that do not have a constant velocity. Thank you very much for watching.